in your grant applications going forward. So, turn it over.
How many do I have? Because I'm notorious. Brian gets on to me for walking, so I got to stay near the mic.
Yes,
Okay.
a little bit,
All right.
but
All right.
there's only one channel.
Okay. Well, I'll try to stay close to the mic.
Generally, this group is pretty good about asking questions, but they're
No. That's the thing is, and I do not. I don't believe in lectures, and right now I'm really frustrating the honors undergraduates because I teach them Tuesday, Thursday, 2 to 3:15, and they just want to sit there and take notes, and I won't let them just sit there and take notes. They need to talk to me about it. So I'll start out with the very first question. How many of you have actually had a formal class in either statistics or biostatistics or mathematical statistics or engineering statistics or financial statistics? And how much did you enjoy that? The reason I ask is this, and again, I will tell you that my first exposure into statistics, and you're going to laugh at this, after I finished the class, I swore to God I would never study this stuff again. It drove me insane. Mainly because it was taught to me in the wrong manner. And until I got to graduate school, and by forces beyond my control, ended up going into studying a Master's of Science in Applied Statistics and then getting a PhD, I didn't really understand the framework because when I started from the wrong perspective. It all started out with a perspective of, here's the formulas, plug and chug. And if you do that, you miss the whole point. So what I'm doing today is I'm just going to say, jettison everything anybody else taught you. Let's go back to, even if you know it, it never hurts to go back to the foundation. Get the foundation correct, and then the house will stand. Get the foundation wrong, the house is not going to stand. Not for long. It may prop itself up for a little while, but you'll always have trouble. So we're just going to back up. And I'm not going to bury you with formulas. We're going to talk about concepts, and we're going to make certain we get these concepts correct. Again, I tell the students all the time, when I teach the introductory biostats, you feel like I've taught you 3 different courses, or 3 different math courses, or mathematical topics, but they always break down the same. Textbooks begin with, here's how you summarize data. Now, I find it very interesting, but one day, sooner or later, we've got to come to a definition of what data really is. But how do you summarize it? How do you calculate the sample means? We're all get buried with all these formulas within the first 3 to 4 weeks, and you're swimming. What does the summation mean? When do I have to square things? Why is it divided by n minus 1? All of that. Okay, that's fine. Summarizing data, descriptive statistics. Then there is this break. It's hard break. Move over into, now let's talk about probability and all these different probability distributions. And then out of nowhere, near the end, we start doing and worrying about p-values. Well, how do those 3 things interact? Why are those the key components? And does it have to be introduced that way? And I'm going to argue no. If I do anything, I want you to, and what I try to do typically is I will introduce the concept of probability first. It's key that you understand that in the absence of probability, I really don't have any need, I have very little need for statistics other than to describe and summarize and generate a report. The key thing is how you use probability and how you not overinterpret probability. My biggest problem is helping people not to interpret a p-value in an incorrect way. I will remind you, I'll talk to you about some of the basic probability distributions that should jog your memory. I like to point them out because they're kind of fun and different examples of where they occur in nature. Then I'm going to emphasize to you the key fact. When you summarize anything from your experiment, you bring me a data set. I sit there and I start asking you a ton of questions. Help me understand your outcome. Help me understand, are you trying to show a difference between two groups? Are you trying to see a difference between three groups? Are you trying to tell me that if I can measure this, then I'm going to be able to dig this down the road? Help me understand all these concepts. The reason I'm forcing and asking those key questions is I'm trying to imagine the probability distribution behind your data as well as the technique that can be used to test your hypothesis. I have to marry the probability distribution to the technique, and then we know the correct path. So to emphasize statistics, sample mean, sample standard deviation, all of the correlation, Pearson correlation, Spearman, every statistic I can give you, I link to a probability distribution. Eventually, I will link them to a probability distribution because I need to know, was the chance of observing that correlation, if, in fact, there's no association whatsoever, is that high or low? I just need a gauge on it. I need a number between 0 and 1 that helps me know, was this likely or not? And how likely was it? If it's very unlikely, then I've got to start concluding possibly there's an association there. Okay? That's the whole principle behind statistics. We'll talk about the central limit theorem, which is the key thing. The reason all textbooks hammer that is it's the first time anywhere in the course, anytime you study statistics, that's the first theorem we hand you that says a statistic from a data set has to behave according to a probability distribution. That's a key thing. So I can tell you how likely was that observing that statistic under a set of assumptions. Okay? The other thing I want to do is I want you to think about statistics and inference always in the framework of a jury trial. When you're doing an experiment, you're actually conducting a trial. You have two beliefs, and you're going to have to pick between them, and you're going to have to bring evidence to pick whether you stay put on the belief of innocence or you switch and move to the idea of guilt, just like you do in a jury trial. But your evidence is going to be probability. All right? Then I'm going to spend a lot of time with key terms correctly defined. Again, got to get the foundation right. The history, it's fun to talk about this. Believe it or not, statisticians are not necessarily always mature. There was a big war at the very beginning, and then we hide it from everybody. Then we'll give you a few examples. Actually, I decided last year when I gave this, I tried to give way too much in the first lecture. So actually, I chopped out power and correlation regression from today, and I'm going to move that into next week so that you get this week to digest it. I'll tell you what I would really appreciate. We'll have conversations as we go through this, but what I would greatly appreciate is at the very beginning of next week, if you've got questions, bring them back. Think about it, digest it, or as I tell the students, let it brew. Let it brew for a while in your head, and then come back with questions. And then, so, every textbook, you come to my office, it's quite interesting. It's just books and books and books and books of math. I've been looking for the perfect introductory stats book for 21 years now. Still looking. Some people say you should write one. The problem with that is everybody ever met that wrote a book. Divorced. Don't want to take a chance. So, but if I had to write a book, I would not do this. They always start out with summarizing the data, and you get lost in the calculation. You get lost in how to calculate a correlation. What am I doing with the standard deviation? Why am I calculating the standard deviation? And the key is you get so bogged down in trying to understand how to apply the formula, you forget what you're trying to do in the first place. Then you get to the laws of probability, then we hit the common probability distribution, binomial, Poisson, binomial, then we're into hypothesis testing. The key thing is this. When we get to marry the three of these things or blend them together, they come together to form what we call inferential statistics. It's the ability to conduct these jury trials or bring statistics to bear to be able to make decision theory. And then the rigor and reproducibility and transparency discussion that I'll have with you in a few weeks. The fourth pillar that the NIH is upset about is statistical rigor and the lack of it. And more importantly, the incorrect interpretation of a p-value. We're going to try to address that today. All right? So this pretty much breaks down into the descriptive statistics, probability, then we go into inference. By that I mean classic null hypothesis significance testing, where you come in and you set up, I believe my mean is, or I believe the correlation is equal to 0 against an alternative hypothesis. I'll try to demonstrate that the correlation is not equal to 0, indicating that there's some form of linear association. Always remember your research hypothesis has to be what? The alternative. When we bring people in for a jury trial, we're not trying to prove that they're innocent. We did that. We'd be doing a lot of trials, a lot more trials. We only bring the trial when we believe there's reason to look at the evidence of the alternative. That's where you place your research hypothesis, always. And I will repeat, always. And somebody's going to come back and go, what if I want to prove that two things are equal? Good luck with that. You want to prove two things are equivalent, I can help you. I cannot prove two things are equal. I can give you evidence that they may be equivalent, but even then I have to write the hypothesis in the alternative. Okay? So what I do when I typically teach is I typically start with probability distribution, start right out from there, and then after getting the foundation of probability, come in and say, probability, and here's the way to always think about statistics in the correct framework. You hand me a data set. I'm going to stop and I'm going to imagine or stop and ponder which probability distribution could have generated this data set. If I have data, I believe it is the child, and I use that word seriously, the child of either one or possibly two or possibly three probability distributions, and I need to decide, can I identify and understand the properties of that probability distribution from its child. Why do I use the analogy of child? Because the probability distribution the data has no choice but to inherit characteristics out of its probability distribution. Why do you care about the sample mean? For no other reason than the sample mean, when you calculate it from the data set, is your best guess of where the center of the probability distribution was. Why do you care about the sample variance? What is variance, by the way? Yeah, sample means just the average. What's sample variance? What's it trying to measure? Dispersion. All variance measures is the average square deviation away from that center. How much does the data fan out? That's all it's trying to do, but we have to square it because we need to make certain that we do not accidentally sum everything back to 0. Just a property that comes in as long as we do squaring of the variance, then we take the square root to get it down to a standard deviation. All right, but those two central characteristics, sample mean, variance, where's the center, how much dispersion, are two characteristics that the data inherit. from the probability distribution. By summarizing those, I can infer, I can judge where the center and how much spread was there being generated by the probability distribution. So this is the way I think about it. This is the way my mind works. I actually think of, you come to me and you're worried about observation, you got your data set, hopefully you're talking about it before the experiment started, and you want me to do this. I stop and I start thinking back up the line, and I say to myself, all right, we have yes, no outcomes. It either has to be you have the characteristic or you don't have the characteristic. We want to be able to say that if I give you this treatment, hopefully it's a good characteristic, that we're going to increase the chances of individuals having this good characteristic. We're trying to create two probability distributions. I immediately think they're both Bernoulli or binomial, and all I want to be able to do is to show that the probability between two different distributions, they do not equal each other, that the second one has a higher probability. That's all I need. That's immediately what I think. But I immediately go, you said you have yes, no, that tells me Bernoulli. Okay, that's where my training comes in. You come in and you tell me you're studying height. Immediately, I'm going to say, when we see the data is continuous, I'm going to start looking at histograms. Why? The data has to inherit the shape of the probability distribution. The reason statisticians study all these different graphs of probability distributions is we're studying the shape, because we know that data must inherit the shape of the probability distribution. If I look at it and I see two modes, very few distributions are actually bimodal. It's a clear indication there's two distributions hiding in the data set. Try to separate them. See if you can disentangle it and identify what's causing two separate distributions. Okay? So this is the way I would like you to start thinking about generally statistics and generally just how you conduct research. The real game to me is to keep the idea of something is generating, and by your very experiments, by either through natural history or by experimentation, you're actually trying to alter probability distributions. If you're successful, you're altering the probability distribution, and therefore you're creating two forms of data. Our job to be able to say, here's the evidence. And that's the whole purpose. And we make it so much harder than that. Bad day for using this example since we're supposed to have rough weather this afternoon. Examples of data. So keep in mind, if there is no variation in your data, you come back and give me a series of constants. Let's grab a couple of problems really don't need me. There must be variation for a statistician's knowledge. Okay? And there must be variation that cannot be explained, or you don't really need a statistician. You go get a mathematician. If we can fit the data perfectly, go to the math department. If you can't fit the data perfectly, then we've got to come to us and do it just back to probability theory. So classic ones that I always introduce to the undergraduates is, I love it every year when we come in and we hear how many hurricanes, the number of hurricanes we're going to have this year. You ever notice that it really doesn't vary much away from change? For a reason. They're just building it off of historical data. They have the same information. The question becomes, has it, and they've gotten very good. The reason we worry about the Pacific so much is now we recognize that the currents of the Pacific have a great influence on how many hurricanes we can have. So we pay attention to that. And if they see that La Nina is coming up, they will adjust their forecast. That's it. They've studied the data and they're using it in different ways. And otherwise, you should go with historical average. Best guess. Biology, I give you this example always: body temperature, blood pressure, weight. Huge studies over the past 30 years, watching Ian Haynes and studying it. You can clearly see the data indicating a change in BMI. But that change in BMI cannot be independent of a change in a probability distribution. So the question is one of the natural factors that have altered the probability distributions that are governing these characteristics within the U.S. population. Great debate about that. Another example about body temperature. What's the average body temperature? Fahrenheit, please. Okay, so here's my question for you. If I came around right now where you took everybody's temperature, 98.6 for all of us? No. And in fact, this is one of the things that's why you study data. My dad passed away about 3 years ago, and we kept having a series of just chronic kidney infections. And we had landed in the hospital. One time we were in the hospital, and I looked at the lady, she gave the nurse scan, and she said Dad's temperature, and I said, the nurse said, excuse me, but can you tell me what Dad's temperature is? And she said, oh, he's fine. He's at 97.5. I said, you need to culture. She looked like I'd lost my mind. And I said, just tell the doctor that I'm concerned. My dad's natural body temperature for all his adult life was never 98.6. Every time we took it, every time he went to the doctor and I was with him, when he was healthy, they would tell me, he's sitting around 96, 96.5, just ran low. And so when they thought he was near normal, that was running hot with Dad. And sure enough, consistently 2 days later, they declined. So that's why it's important to know the natural history of the data. Because I knew Dad's probability distribution. Sure, Dad fluctuated, but that was never a 98.6 consistent. Never. Neither was Mom. I don't know why, but the rest of us seem normal.
What about you, the child?
Huh?
You inherit? What about you?
The data set.
It seems to me, I do that. I say pretty much 98.6. So, I also,
As a data set, you're not very representative.
well, you see, but the catch here is the reference, and it's key. That's why you meet with the statisticians, is so that you know the exact reference you should be. If you're measuring me over time, and the emphasis is me over time, I do not need to be compared to the general population. I need to be compared to my within variance, not the between variance. Between variance is only useful as cross-sectional study. Longitudinal study, the variance that measures, that matters, is within the individuals. In a few weeks, I entertained the undergraduates by bringing them all a bag of M&Ms, chocolate, no peanuts, mainly because basic probability distribution. You know what the multinomial is? Ours does not, the company does not reveal the distribution of college working. We don't know what the prevalence of blue M&Ms are. They don't reveal it. They don't reveal what's the prevalence of the red. They don't do it. I don't know why. I don't know what this is secret. But it gives me a very good teaching example because I bring in 50 bags. We're undergraduate classes around 50, 55. And I say, all right, let's get the data. Because all those bags are inheriting the probability distribution, which is a multiplier. And by the end of the class, everybody's still got a shot behind, but we can estimate the prevalence of blue M&Ms to within plus or minus 1%, just based on plain and simple names. So from the data, I can tell you very closely what the real distribution hiding behind it must be. Because there's no other way. I mean, go ahead. The diagram is a great teaching example. That's the classic multiple. Okay? Computer chips, engineering, the number of flaws on a computer chip, that's a Poisson distribution, the number of shipwrecks per square mile of the bottom of the Atlantic follows the Poisson distribution. So the game is when you tell me the characteristics for me to help you move back toward what probability distribution should we be studying, and what are the assumptions behind that, and how do we show it? All right, variation underpins everything. That's why statisticians, when you come to me for a power calculation, we'll understand in next week what power really is and what it's not. The first thing I ask you is not necessarily how big of a difference do you expect to have. Or two. But I can't do anything until I have something to do very important. Okay, so we there's historical estimate, but key thing to keep in mind, clinicians tend to think about what's the difference or the gap between the two groups. That's only half of what I need. I need to know just how variable, how noisy is the data. As soon as I get variation, then I've got probability, and then I have to start talking about that mathematical model that provides the tendency and dispersion in your data. Okay? There we go. One of the examples, continuous normal distribution. Typically we think about the normal distribution, the bell curve. IQ is designed, IQ tests are designed to be centered with a mean of 100 standard deviation of 10. So if you see, we do just population studies, you're going to see the bell curve. Poisson distribution is the rare one. It used to be called the AT&T distribution. If you're talking about something that is coming in over time or over space, you can say per something is a rate. How many texts will my daughter send me per day? Usually per hour, actually. I don't know how they have their phones at school, but sometimes it does. The number of shipwrecks per square mile on the Atlantic, the number of unexploded bombs per city block, London, they're still out there. So those types of things. Poisson, the first time we found the Poisson in biology was the number of live yeast left in a fat deer after fermentation. So that's places where you see that binomial is actually the binomial is typically still my favorite because it's the easiest thing to design. You gotta give a study around because it's just a yes or a no. So I just really need you to tell me two things. What's the probability in this group? What's the probability in the other group? Design a study very quickly about what you're anticipated. And like I said, the multinomial bags of M&Ms, genotypes, haplotypes, those tend to be multinomial distributions that I'm working on. Okay. Binomial, only two possible outcomes. Multinomial, more than two. Okay. Even has more than two possible categorical outcomes. So, let's talk. You like talking to me now. What do you think about personalized medicine? How's that feel? What do you think about personalized medicine?
Depends.
Hmm?
It depends.
On what?
Person.
The person. Is it me or not? Is it me or not?
Precision medicine.
Hmm?
Something like precision medicine.
Here's my problem with it. We've always personalized it. We've never said to anybody, you're going to get 5 milligrams no matter what. We never said that. We have allowed variation in doses, but what we've done is we've tried to find our path by studying what's going on in the general population and then adjusting to each individual to try to optimize it. My understanding of personalized medicine is that I understand we want a greater shift in the optimization. We can't go to personalized medicine without first still studying the population. We may be able to bring in further characteristics of the individual to better refine what is best for the individual, but we still have to start with the population. And I wonder about that because the reason I bring that up is I don't study data points. You send me a data set of 400. I may look to see if there are 2 or 3 outliers, but I don't go line by line looking at the data. I don't. That's not what I need. I need the summary of the data. And remember, when you came to me and said, Dr. Ed, or David, the way called Dr. Ed, what am I doing? What are the 3 things you really need to know about the probability distribution? All I really need to know is where is it set? What's the spread? What's the shape? I don't even need to know its names. I don't have to correctly identify it by name. You can give me those 3 things. I've got enough to work with now. Now, the reason you bring me the raw data is because I can abstract those 3 pieces immediately from the raw data. You bring me the mean and the standard deviation, I am a little bit handcuffed because I don't see the shape. But there are ways around that. That's the only reason we teach these 2 formulas at the very beginning of the class, is because I need those 2, these are my 2 best estimators of what's going on in the probability distribution. Tells me where the center is. X bar is just a measure of central tendency. That's all it is. Tells me where the center of gravity is. That's all. Tells me no, this is dead center. Now, the problem with sample mean, sometimes we choose to go with the sample median instead. Because if you have outliers, 1 or 2 outliers can pull the mean, sample mean around. The thing about outliers, black holes, they have extreme gravity, so they are able to distort your variance and your mean. That's why we come up with what's called robust measures of central tendency and dispersion. That's why we teach sample median. That's why we teach interquartile range. Those 2 things, they're not going to be influenced by extreme tendency. Studying the data, get a good judgment which of those approaches I should go. That's all. But typically, I'm immediately worried about the measure of central tendency, and I'm also worried about how much dispersion. Okay? Or there happens to be in the data set. Because the data inherits characteristics from the probability, the statistics can be used to infer, to guess the characteristics of the probability distribution. Sometimes, under certain assumptions, you know the probability distribution that governs your descriptive statistics. Keep in mind this. Cool fact. Harvard for 2 years refining over the past 2 years what every undergraduate class, they went through the required set across all degrees that they're going to give an undergraduate degree. All of us had to take English. All of us had to do those certain things. We couldn't get out. We all had to take history. And some form of history. We couldn't get out, right? Depending on your major, you might be able to get out chemistry or physics or calculus. They did a 2-year review. They added 1 class to every degree. Well, they didn't drop 1. They added 1. Introductory statistics. Because think about it. You go to yourself up here to the next statistic. You go listen to the financial channel right now. They're going to give you an employment. Right? Is that number right? How precise is that measure? How good is the estimate? That's the question you've got to be asking yourself. Well, to be able to even ask that question, you've got to comprehend 1 key essential fact. This is the only fact I try to get across in the undergraduate program. The whole semester, you get 1 point across. 1, statistics follow probability distributions. The statistic itself, not just the raw outcomes, but the statistic that you have from the data set is a realization of a probability distribution. And you can say how likely or the gods of probability hand me this if this is true. Okay? Now here's the mind-blowing fact. You could get data from a Poisson distribution, and your descriptive statistic doesn't have to follow a Poisson distribution. You can get binomial data. Summarize your descriptive statistics, and it doesn't follow a binomial. It is dependent upon the statistic that you use causes you to fall toward a probability distribution, and it can be completely independent of the underlying probability distribution. That's why we all teach the central limit theorem. That's why it's so key. The central limit theorem simply says this: regardless of the underlying probability distribution, it doesn't matter what generated the data. If you come to me and say, Dr. Redden or David, we need to study the sample mean. Hey, my life just got really easy. My life got a lot easier. Because as long as it's generally a bell shape or close to it, or you give me a large sample size, then the sample mean, the sample statistic, had to be drawn out of a normal distribution. It's that easy. And I can, in the undergraduate program, I will run simulations. You should introduce a simple limit theorem yesterday. Tomorrow, I'll just run simulations and I'll say, look at this crazy data. I want to say, now I'm going to make a computer play the game of 1,000 experiments. Give me a sample mean. Run the experiment, generate the data, hand me the sample mean. Do the experiment again, hand me the sample mean. And I will generate 1,000, 10,000 sample means. I'll say, okay, let's just go to the history rate. I'm going to start out and say, all right, we're going to be studying Poisson. Let's go get 50 Poisson observations. Calculate the mean. Over and over. Yes?
So when you said it doesn't matter what generated the data, I'm assuming that there's some limits to that. It's not about sampling.
It is all, what matters is the number of observations you give me. Generally, if you give me 30 or more, and I calculate the sample mean, I'm safe.
So it doesn't matter if that sample is a convenient sample, a random sample. Okay.
That affects the variance. That does not affect the distribution itself. Those types of facts, whether it was a convenience or whether, and so that's why we're very careful. One of the first things I'll ask you in any consultation is simple. Are you looking at me one time or are you looking at me 3 times? If you see me over time, multiple times, that changes the variance calculation. It doesn't change the property of X bar. It changes the variance estimate. Okay? And that's why, statisticians, you'll hear statisticians, sometimes we try to make ourselves sound rather smart. You'll hear me say, as long as the observations are independent and identically distributed, and you give me a large sample size, X bar will be approximately normally distributed. The key terms are, I don't say anything about the probability distribution. I said independent and identical. They're all coming from a common, and there is no correlation among them. So David, knowing David's blood pressure should not be able to predict my blood pressure. That's what I mean by independent. That's all it is. And after that, I have to be mindful of cross-section longitudinal. But a general fact, one observation or 30 observations drawn from a single probability distribution, average, X bar is going to behave normally. Period. That's the key thing. Why is the central limit theorem so important? It tells you one simple fact. I don't want you to memorize the central limit theorem. You're on the undergraduate program. What I want you to understand is the central limit theorem tells you a statistic a descriptive statistic summarized from a data set can be linked to a probability distribution. So I can say, based on that, was this a rare statistic? Was this an unexpected statistic? Or was this something that, we had a 50% chance? Not that surprising. Is it rare? Okay. The other thing that's key in the social limit, there's really just two key points in the social limit theory. X bar links to a normal distribution. And the bigger the sample, what happens to the standard deviation? What happens to the precision of your estimate? The precision increases because the standard deviation is falling. You keep dividing. If I put 100 there, you're dividing by 10. If I put 400 there, you're dividing by 20. Okay, if I put 900 here, you start dividing by 30, and you're slamming, you're making a more precise. X bar is becoming a much more precise estimator of where the mean would fall. Okay? So if you look at their ability how to estimate the mean of the probability distribution precisely. All right, I see some concentrating on what are the questions? We've got questions at this point? Oh, my goodness. All right. Questions?
It can't be that clear. How are you, I'm a little bit confused.
Okay.
How are you getting multiple means from one?
I'm not. And that's the catch. This is where everybody stumbles a little bit on the social limit theory. Okay? From one experiment, I get one sample mean. But that one sample mean can be linked into a probability distribution. To be able to show the shape of the probability distribution, I have to start imagining I get to do the experiment over and over. And only then would I see the shape of the distribution for the X bar probability distribution. They will consistently be one. Okay? So you're exactly right. When people come into the clinic and they bring me the data set, I get one sample mean. But because of the theorem, I know that one draw came from this probability distribution. Yes?
The central limit theorem also says that you have a number of 30 approximates the population distribution. Where did that number come from?
One more time. Where did 30? 30 is just a rule of thumb. Okay? If the underlying distribution is already symmetric, so that it's already got symmetry to it, and an example of that would almost be like the binomial, where you've got a 50-50 probability. It's a symmetric distribution, actually. If it's a symmetric distribution to begin with, that underlies the data, I can get by with 10 to 15, and I can already approximate. But that's just a rule of thumb. Yes?
So I always thought that standard deviation meant you have a group of people, for instance, you have one standard deviation, 2/3 of them are going to fall.
You're upset that I said standard deviation up. Go ahead. You're exactly right. Go ahead. You're right.
Well, but is this saying that standard deviation means if you were just to do the experiment over and over and over again?
The answer there is this, okay? Standard deviation is typically always based on and introduced as studying the population. When we go to sampling distributions, and we use the word sampling distributions to represent, we have now gone to study the distribution of a statistic. We flip the word. We introduce standard error, and it drives everybody insane. Standard error is a standard deviation. It's still a standard deviation, but it's a standard deviation calculated under the theorem.
So that's what this means, the standard error.
Yes. But it's still, the standard error is a standard deviation.
Right, but not in the
Population. but it's from the sampling distribution. All distributions have variances, therefore they have standard deviations. We give a special name to the sigma over the square root of n, and we rename it standard error, even though it's technically a standard deviation.
Right.
Okay. All right, so I belabored that point. Let's do this. Let's do the break now. Okay? Y'all are going to do one break, right? You're not enjoying that. You're doing a break. Let's take a break now. Come back at 9. Check your email, do that stuff. Come back at 9, and then we're going to really hammer down on the foundations of these matters. Okay? And then we're going to make sure you never forget what a p-value is. So hopefully when you meet with Cindy at 11. I saw Mike's email. What was that?
Well, and I replied back to him, and I said, I'll see what we can do. I said, but I really only have data from February on, so if you're looking for the entire year of 2016, I said, you may want to contact Michael Hill, because he's the one putting together the tracking logs for us. And he could send you a comprehensive one. Yeah, I got it.
Don't leave that. But it's, you're getting
Be careful.
Oh. Okay.
Well, that's really good.
Yep. You are not. I didn't know if I and you've been doing this a lot of it, and it's been posted for your presentations, yes. Okay. Yeah. Yeah, I think that, let me know if that's missing that. There you go. Right. She said,
Okay. Let's get the foundation of the whole idea of hypothesis testing down. Every bit. And let's get the key terms that these are the points that have to be made in every journal article. We have to produce the evidence. But let's step away from science for 1 minute. In a jury trial, there are 2 hypotheses, right? There are actually, the way to think about it is there is a assumed truth, and then a possible research conclusion or a possible, let's call it a hypothesis. What are they? And which one is which? What is assumed to be true? The person is innocent. The alternative is what? Say it.
Guilty.
Thank you.
That's charged.
Guilty as charged. What do you know about those 2 things? They are what?
Mutually exclusive.
Great term. Mutually exclusive. That means that there's no overlap. There is no gray area. You must fall on one of the 2. What else are they? The other term that says this, mutually exclusive, and they're exhaustive. You've got to be in one of those 2 corners. You've got to be in one of those areas. You cannot, yes, we get mistrials and we get a hung jury. It's not because there's a third option. It's that it can't decide. There's the outcome. There's only 2 possible. It's binary. It is decision theory. This or that. And this is opposite of that. Right? So, prosecution brings evidence of what? They're not bringing, the prosecution is not bringing stuff in to say, hey, yeah, this looks like innocence to us. Right? Evidence to a statistician, when you bring me your data, what's your evidence? Think about it for a minute. What's your evidence? I'm going to help you set up a jury trial. I'm going to put your research hypothesis as the second, the alternative, the guilt. I'm the prosecutor. What's the evidence I have? The data. The data is going to be the evidence that I get to use. What do I need? I need evidence beyond a what? Reasonable doubt. You ever wonder what a statistician means by type 1 error? Type 1 error is just my definition of reasonable doubt. I need evidence beyond reasonable doubt. A p-value is probability. Alpha is reasonable doubt. I compare the 2. That's all I do. I look for evidence, which is a p-value, beyond a reasonable doubt, and we decide what a reasonable doubt is. Just like a jury trial. At the end of a jury trial, what does, has anybody had to serve on a jury? Isn't it fun? Or the person hands the verdict to the bailiff takes it to the judge reads it, hands it back to the bailiff, comes back to the jury, so the jury finds the defendant, what? Let's just say that the person's not going to prison.
Not guilty.
Why do they not say, we find the person innocent? Why don't they say that? They never say it. They say not guilty.
So we're looking to prove.
You cannot prove what you assumed. You can never prove what you had to assume to do the trial. So when you fail to conclude your research hypothesis, you will never say in the journals, I proved no difference existed. Don't say that. You can't, because you cannot prove what had to be assumed and done, the evaluation. Okay? So, null hypothesis. The null hypothesis in the jury trial, person's innocent. Null hypothesis in your research is, you're wrong. This does not predict that. Your drug is not more beneficial than this drug. It's the null hypothesis. It's the absence of what is the opposite statement than what you're trying to prove. And you've got to produce evidence from your experiment, data from your experiment or your investigation that can be summarized to provide evidence toward the alternative. So, the null is the key thing, though. Please read my statement about the null hypothesis. It's simply that will be used to evaluate the probability, key thing, all I care about the probability, of observing the data from your experiment. Okay, so when the jury starts studying the evidence of prosecution, what does it mean when we say, assume that the person is assumed innocent until proven guilty or declared guilty, I should say. Or declared guilty. What does that really mean? Conceptually, what does it mean? You get what that conceptually means, you'll never forget what a p-value really is. What does it mean? What does it mean when we say the person is assumed innocent? You know what it means? It means much more than, I'm going to start with the belief they're innocent. It's much more than that. What does it mean? It means when the prosecution gets up and says, hey, this person was on the same city block as the person who was murdered. Okay? Let me assume the person is innocent. What's the chance they would be on the same city block? Well, there are 5 restaurants there. It's one of the most popular districts. People like to eat there. Assuming the person is innocent, is it likely that they could be in the vicinity? Me being rational, yeah, I like steak. I might go to the same restaurant. All right, so that's not convincing, given I'm holding the belief of innocence. Well, the cell phone tower, the cell phone says that they texted that person 5 times that day. I'm still not very convinced me, assuming they're innocent. That person may have been doing business with the person. They may be friends with the person. I don't know. That's not going to convince me. Under the belief of innocence, that person could still be innocent and have tons of communication with the victim. That doesn't mean they murdered them. Okay? The person's blood is in their car. There is a knife with their DNA, the victim's DNA on it, and the person's DNA on it. There are bloody fingerprints on the white Bronco. All these things.
And the glove in your trunk.
There's gloves in the trunk. The mathematical probability of having the DNA match is being being struck like being 14 times in one day. Now, let's see. Is that preponderance of evidence likely to occur around an innocent person? No. you see what you're doing? You're comparing the preponderance. How likely is the preponderance of evidence given I continue trying to hold this belief? That's what p-value is. The p-value is the probability of observing the data with me trying to marry it to a probability distribution that says, no, this belief has to be true. And then I'm saying, well, if this belief is true, this evidence matches that belief. Or would likely occur under that belief. Could occur under that belief. But then I also have the ability to say, under that belief, this data should not occur very often. Is that so extreme for me to be able to reject the null hypothesis and now do a liquid search? Same idea. Is the preponderance of evidence so extreme that I need to be able to say that's just not compatible with the belief of innocence? Now, let's give up the belief of innocence and declare results. What I do. That's what I do with everybody's data sets. Exactly what I do. And at the end of the day, do I make mistakes? Oh, yes, quite often. Yes?
Well, I'm not trying to be able to articulate this well, but in thinking about the analogy of the evidence for a charge of guilty, at some point there's a tipping point. And is that tipping point in science what you choose as your value?
No, I don't choose the p-value. The gods of probability give me the p-values.
No, I mean,
But they give you and I jointly choose the type 1 error rate.
the alpha.
The alpha.
Okay.
There it is. That's the threshold.
Okay.
That's the beyond reasonable doubt.
Okay.
In fact, I'll ruin it right now. Let me jump ahead. When we get here, when I teach the students in undergraduate, let's get through all that. I'll come back to all that. Very much. I make them read this. Evidence beyond reasonable doubt. That's exactly what that statement says. P-value less than or equal to a type 1 error is equivalent to a statistician declaring evidence beyond reasonable doubt. But unlike a jury trial where everybody in the room or everybody in the jury has to come up with their own individual reasonable doubt, typically in science we have put a number to it. Typically we put a 0.05 to it, and it has no scientific justification whatsoever. It's just tradition. You should not be grounded in that. I'll explain that to you in a minute. All right, but always remember, the idea of the p, the reason is the p-value is the evidence and the alpha is the reasonable doubt. Small p-values indicate rare events. You want evidence that is rare when the person is innocent to be before you jump to guilt. Same thing with the data. You want rare data that would occur under the null before you jump to the guilt. All right. So we got the p-value, the type 1 error rate just said this, the probability of observing the data, this is my evidence, this is my reasonable doubt. This comes from the data, you have no control over it. It is generated by the experiment. We decide that jointly and should be decided before the trial begins, before your experiment begins. It is not universally 0.05. It is not, should not be. For genetic studies, we are looking at hundreds of thousands of markers now. 0.05 is foolish. It's got to be much lower. Much lower. I'll tell you where it came from in just a minute. Typically, I rely my approach now, much more than anything else, is we will discuss what the alpha should be before we do the experiment, but at the same time, I hand the p-value to people and say, let's discuss it. You'll understand where I'm coming from with that in just a minute. Power, I mean, what you won't. Power, we'll get into this much more next week. Power is just, you won't, if, what would it mean when we say the prosecution has a powerful case? What does that mean? What does it mean? It means that there's so much evidence that it's almost inconceivable that the jury is going to be able to hold to its belief of innocence. Same thing when I say I've designed a powerful study. If you in fact are producing the effect, I have arranged the trial through the design, the sample size, the way we're conducting the experiments, that if you are in fact going to produce this difference, I'm going to make it almost certain that the p-value is going to indicate. But not rigging it. I'm just designing the trial to optimize your chance. You still got to produce it. And if you don't produce it, then I got to ask myself, well, I set the decks for you. I mean, I set the table. It's not there. Does that prove it doesn't exist? No. Which means that I don't have evidence for this. Correlation is, just keep in mind, a lot of people will say, well, correlation measures association. Please understand, correlation for a statistician means a linear association. It means I decided to try to fit a line between two variables. Just like you do in algebra. You're trying to fit a line. There are other types of association with curvature that I might need to fit. That's why it's important for us to discuss the nature of your experiment when you decide. Equal that line with it, perhaps I should be putting curves in. All right. Even with the honors class in the undergraduate, my job up until spring break is just to make certain we don't come. They're all like, what are we doing here? I mean, this is coming too fast, too furious. And I keep telling them, as soon as we get to spring break, you just got to remember the rest. You just got to remember the scientific method. Has anybody heard being in high school being learned the scientific? What was the scientific method? Anybody? What was it? State the hypotheses, collect the data, analyze the data, draw a conclusion. All right, that's my day job. There it is. That's it. I help you state the hypotheses. I help you collect the data. I bring the statistics to analyze the data and draw a conclusion. So over and over, all we do, throughout all these consultations, all the stuff that we do with the bird, we help people state the hypotheses. We help you know which is your appropriate evidence. What test statistic should we use as our evidence? Then we come in and say, based on the evidence, and we compare it to a type 1 error rate, if evidence beyond reasonable doubt, we reject the null and include the alternative. That's it. That's all I do. Do it again and again. Different flavor, different options based on the experiment, but it's consistently that. Let's set up the null and the alternative, run the trial, summarize my evidence as p-value, judge it as beyond a reasonable doubt, draw a conclusion. My conclusions are either I fail to reject the null, which is equivalent to saying not guilty, or I reject the null and conclude the alternative, which is to say we've got evidence that your hypothesis, your research hypothesis, is correct. But there's evidence for it. It doesn't mean that I can prove anything. As I've said before, if you want a proof, you might want a mathematician. Okay, where did all this come from? This is the part we hide from everybody. This is the fun piece that unless you take the history of statistics, nobody tells you these things. The very first class I took, you gotta remember, I finished my bachelor's in mathematics in '91. I had 3 statistics courses, 3 full statistics courses, a full year under the quarter system. Full year. Get ready. This is '91. to me in all three classes. P-value. What? They did not introduce the p-value. Not yet. They did not discuss the p-value. R.A. Fisher, interesting guy. He's the guy that came up with randomization for us and told us how important it was. He was also an avid smoker, and until his death, he refused to believe that there was an association between smoking and lung cancer, because he did not know one would provide him a randomized study, and therefore he consistently argued about it. And he was stubborn. He was a difficult person to work around. But he is also the father of modern statistics, because he gave us the p-value. And he also gave us estimation techniques that we have to use that are typically called like maximum likelihood. He did a lot of the theory. Here's how he did all his experiments. He set up a null hypothesis. He calculated a p-value for that hypothesis. And he reported the p-value. And he walked away. And then went to his next experiment. What's missing? What's missing?
A conclusion drawn.
Right. He didn't draw a conclusion. So what else didn't he give you? One more. What you brought up a minute ago. Where's the type 1 error rate? Where's the alpha? Where's the alternative hypothesis? This is all he gave you. This is what he was teaching everybody. Right? Here's his rationale. He felt like, to his credit, the scientific community, being as intelligent as it is, should not be forced to hold one standard of beyond a reasonable doubt. Jury trial, in a jury trial, every person on the jury has to define that for themselves, right? And then there has to be a consensus among the community of the jury. And it can't get there. So he wasn't giving people alphas or type 1 error rates. Okay? And that's why, since really all you need is a null hypothesis for a p-value, you don't need the alternative to calculate it. He felt no need to state the alternative for a type 1 error. So he'd come back and say, all right, the data's compatibility with this belief by probability is 0.04. And leave it to you to say, does that convince you, yes or no? There's a 4% chance. If I conducted this experiment 100 times, literally I would get possibly 4 experiments or fewer that would actually have this extreme data. Is that convincing enough for you to give up the belief? Oh, now we've got a p-value of 1 in 10,000. Is that enough for you? And you just leave it to the members of the scientific community. There is some value in that approach. Okay, there's great value in that approach. Because I conducted a $2 million study with an investigator several years ago, and the person started to bawl when I revealed the final p-value for the primary analysis was 0.051. Now the problem with that is, it's an arbitrary line, folks. I got it published, no sweat, went right through the journals. But in her training, if it doesn't get below the line, it ain't going to convince anybody. And I'm like, it is what it is. Let's let the scientific community conclude. Okay? So the danger of the p-value, this is what's going on in rigor and reproducibility, is people thinking that, oh, 0.04 is very convincing evidence. Well, not really. Not really. Depends on the situation. Like you gave me a point of 4, I got some evidence, but I'm going to go find some other people who are trying to replicate that experiment. I want a bigger, and the next one I want it to be even bigger. Right? So, that's what he did. Now, remember, believe it or not, statisticians can be difficult people. There was this other group. My wife was very happy that we did not have a son. I have 3 daughters. The other group that was developing statistical theory at the same time, this was all 1910, 1920s, 1910s, 1910 to 1930. All this was going on. Was Jersey Neyman and Egon Pearson. I was going to name a kid Egon, but I mean, that's my wife. We didn't have a son, so it didn't work. They proposed the following thing. They said, no, you got to have a null and an alternative. You got to do it just like a jury trial. You got to have this and that, and make them opposites. Make it as opposite as going left as it is going right. They're doing decision theory. They wanted the type 1 error rate. Then, so they are the ones that said, before you start the experiment, you got to accept that you're going to have a 5% chance of being wrong. You're the 5% of the time you should go left, and you're going to go right instead. You're wrong. All right. Using that to find a rejection region, so they would draw out the curves, and they would draw regions in the probability distribution. And if you got data outside that, inside that region, so extreme that you're in the boundaries, they did an apt name of naming. They did a good job of naming it. It's called the rejection region for a reason. You get into that region, you're going to reject and go to the alternative. Otherwise, conclude the null. And notice, they were bold. They said conclude the null. In their papers, they would say, we proved the null. Okay. I've never been comfortable with that, but under their decision theory, since they're just saying, I've got to pick left or right, it's equivalent to saying, I picked this instead of picking that. Now, where did this come from? And what's missing? Fisher, where's the alternative? Where's the significance? And notice the image had nothing to do with the p-value. They did not want to summarize it as evidence. All they were doing was decision theory. We're here, we do this. We're here, we don't do this. That's it. These people hated each other. They're the history of statistics books that are out there. They're interesting. It's not a great book unless you're a statistician. Called Lady Tasting Tea that records their feud. Folks, it was a feud. They were at one point at the same university. In England, Neyman and Pearson got so frustrated they decided they had to relocate to Berkeley. Not just leave the university. They left England and went across and started all over. They had nothing to do with each other. There's a story of Pearson giving a talk in Paris on one of his theories. He sees Fisher coming in the back of the room, and he's just prepared for a huge fight. And everybody notices Pearson just start pouring sweat. Here they go again. And finally, he sits down. Fisher leaves the room. One of the other presenters puts his hand on Pearson's shoulder and says, calm down. Fisher doesn't speak French. The whole presentation is in French. They really, really did not like it. It was personal. Fisher was over the journals that published stats theory. He blocked Pearson's results 18 years because he was the editor. Came in for Pearson, rejected. Yeah, professionalism 101. Way to go. So, where does our stuff come from? Where's the stuff I teach you? It's a bastardized version of the 2 approaches. What we did in the early 90s is we took the 2 and said we no longer care. They're both dead. They're long gone. and we mixed the two procedures together. We came up with what we do now. And a lot of the time when people get confused, it's because of the way we mixed the two procedures, the two philosophies together to try to come up with a middle ground. That's why people who use p-values have a really hard time understanding statistical power. But if you understand what Pearson was doing, power is very clear. Is a binary system. You've got two distributions. Which distribution has more area in the curve? That's all. So, please remember, talk to a statistician. Here are the problems. Here are the big things that are a problem. Everybody's got in their head 0.05, 0.05, 0.05. I'm guilty about it. When I teach new graduates, what do I put on the board? 0.9. But if I started putting 0.01, they're going to get stuck on that too. Where did 0.05 come from? 0.05 came from the fact that after years of getting hammered, Fisher finally said in a footnote of a paper, what is convincing evidence? For some, it would be 1 out of 100, 0.01. For others, it may be 10 out of 100, 0.1. As for me, 5 out of 100. Boom! It's now gospel. It's in stone. It's 0.05. That's all the evidence we can find for it. So you said that. That's it. But if we're going to use the p-value as evidence beyond a reasonable doubt, you got to say what the evidence or what is reasonable doubt. You've got, and this is where I may not make it through all my slides. It's okay. I have a couple more weeks. If you walk out of here with one thing today, one thing, I need you to understand a p-value is evaluated under the belief the null is true. The same thing as a jury trial. The evidence is evaluated under the belief the null is true. The person is innocent. Okay. How compatible is the evidence given I hold this belief? That's all it is. Now, what I'm about to do is we do this. This has been done over and over for several decades now. We just start giving true-false statements. The p-value is this, the p-value is this, the p-value is this, the p-value is this. And trying to see among the scientific community, do people recognize when the statement is just bogus? And unfortunately, the success rate is pretty abysmal. So, let's play true-false. Is that statement true or false? False. False. Very good. I'm starting easy. Don't get caught. Starting easy. What's wrong with it? We can't prove it. That's it. It's not proven. Not proven. I got a question for you. Have we sent innocent people to prison? Yes. Absolutely. That's why, keep in mind, that's why it's a type 1 error rate. This is the one that we do not want to make. The worst thing that our judicial system could be doing by our philosophy is sending innocent people to prison. We incorrectly rejected their innocence and declared them guilty. Now, we want that to be rare. So we want the type 1 error rate to be what? Low. By lowering it, if you go p-value less than or equal to alpha, lowering the alpha means you must have much more convincing evidence. It works. But you got this does not acknowledge the possibility of type 1 error. It's false. Okay, we're going to slowly ramp it up. My colleagues, Brian's not here recording this, is he?
I don't know if it's recording.
The problem, I have researchers that will not be named who, despite a 15-year collaboration, write this in papers and I have to strike it every time before it goes to, before it's sent out. So I just told you it's false. What's wrong with it? Everybody, if you want to prove, get me a mathematician, please. If you want to prove, get me a mathematician. If you want to discuss truth, I'll take you to the philosophy department. I'll get you a philosopher. I'm not here about truth, and I'm not here about proofs. I'm here about this is the evidence, and we make decisions, and we will make mistakes, and we're not, there is no probability of truth. Okay? What the p-value is saying is the probability of seeing the data is unlikely. It's about 1% if the null hypothesis is in fact true. That's what the p-value is. It's a conditional probability. What's the probability of seeing my data or data even more extreme when I hold fast to the belief this is true? I can calculate the probability of that.
Is that where you would say cannot be rejected?
Hmm?
Would you say cannot be rejected instead?
At this statement, I'm going to get, in a minute, I'm going to get to the correct one. I wouldn't let anything near this go out. Near this, because when people, and this is the part you didn't think was preview actually, when you submit a grant to NIH and they come after you about the power calculation, 99.9% of the time is because you didn't provide enough information. Not that your calculation is incorrect. It is probably correct. You just didn't give the details. This is not giving the sufficient details. And it's leading to a misinterpretation. What about that? I have researchers who want to say this. All that is false. You can't say you disproved the null. You can't say you disproved the null. You can't say you proved the alternative. It's just the flip. Yes, 0.01 is a convincing level if you're using alpha equal to 0.05, but it's not a proof. What about this? This is slippery slope. Psychologists do this all the time. Forgive me, girl. My wife's a psychologist, but she swore off statistics.
You can't say something's right or wrong. You can describe two distributions.
Well, I can say that there is, in any experiment, a chance that I'm making a type 1 error. So I do set that. But the problem here is you're taking the p-value and saying it is the chance of a type 1 error. That's not it. Those two things are separate concepts. In psychology, they like to try to put the two together and just say, okay, it's significant at this level. No. It can be significant in multiple other levels. You've got to disentangle those two. Okay? So do not be tempted to say that your p-value is your type 1 error rate. Those are not the same thing. The p-value is always the probability of observing that data or data more extreme under my belief. Under the belief the null is true. Just like a jury trial. So it's false. The probability of the null hypothesis is true given the data. This is getting closer because I say given the data, but it's backwards. You flipped them. Boy, so many people want to do this. People are so eager to say something about the truth that they just keep tripping themselves up. No. This is false. What about that? Y'all have my notes. I mean, Jim gave them to you. You can just flip one page further. You can just look at the next slide. You'll be all right. That's true. That's okay. But that still doesn't draw a conclusion. It's just summarizing the state of the evidence. Okay? So the p-value is there based on this, the probability of observing the data, or it's 1%. You had a 1 out of 100 chance of getting this type of data or something more convincing. That's it. It's just the sky is blue, data's bold, probability of this data is 0.01 under Michael. That's all it is. Now I leave it to you to make a judgment. Yep.
All right, this may be very elementary, but could you explain, I haven't this issue, could you explain how type 1 error and p-value are not related?
They are related. They're just not the same concept.
Okay.
They are related. I don't want to imply to you they're not related. Okay? So let's get to this. I start my experiment. I say we're going to have an alpha of 0.05. Okay? Try to unpack the confusion. Before I start the experiment, what is my chance of just when the null hypothesis is true, the null hypothesis is true, what is my, before I even collect the first piece of evidence, what's the chance that I'm going to reject the null hypothesis? If it's true, 0.05. I'm saying if I get any data, that is in a certain region, if it's rarer than 5%, I'm going to go. Now, suppose the null hypothesis is true. I do this 1,000 times, right? How many times am I going to reject the null hypothesis? 50 of those experiments I will pay. I've got reason to conclude the alternative. It's a mistake, but it's a long run chance. Okay? So it is the line in the sand. 5% of the time, when the null is true, I'm going to make a mistake. That's what the type 1 error is. Now look at this p-value though. The p-value comes back and says, all right, the probability of having this data, the realization out of the experiment, is about a little bit better than 1 out of 100. Well, because this is smaller than that, evidence beyond my reasonable doubt that I said I would reject. Let me ask you this. Suppose I had decided 0.25 or 0.025. 0.025 is my alpha. What would this change? No. What if I brought it down to 0.015? See, this is what psychologists do. Psychologists keep bringing the alpha down until it touches. And then arbitrarily say, okay, well, it's significant at this level. The problem with that is it's not disentangling the two pieces. Okay, it's saying, it's actually blurring the line. They have a point, but it's moving away from the practice. I don't think I've done a good job of explaining or taking away your confusion. Let's try it again. State your question again.
So I guess the heart of my question is I want to understand how to properly understand p-values or type 1 error.
First,
How they're being and how they're not.
let's get the p-value down first.
Okay.
The p-value is the evidence. Go ahead.
Well, I was just going to ask a question that makes my clarify for you if this is correct. Is it true that alpha is something that's purely a product of your study design?
Yes.
So you're not resulting in alpha. Alpha is part of your study design. And then you have this probability that results, and you try to see if it's greater than or less than your study design, actually.
All right, so
That's right.
that is correct, and maybe this will help a little bit. This is where things have gone really, and understand, I'm in the camp that the tools in a lot of ways are being misapplied, and the way I'm trying to fix it, just know what the p-value is. It explains the p-value correctly. Let's back up a little bit closer to Fisher. Talk about what the p-value is, and then, knowing that that's the evidence, say, does that convince the jury? Okay, so I'm starting to fall more and more on Fisher. Though I do like Pearson's approach to power. Here's the problem with psychology journals. I don't mean, do I have a psychologist there? Here's the problem. I should bring you next week from the psychology journals. What they love to do is they give you the p-values. They give you this long list of p-values. And by the p-value, they will put 3 asterisks, 2 asterisks, or 1 asterisk. 1 asterisk means it's below 0.1. 2 asterisks means it's below 0.1. 3 means it's below 0.1. That's all they're telling you. So what they're doing is they're shifting the sand, or they're shifting the bar from test to test to test to test. And that actually just really thwarts the approach of this of using the p-value. Needs to be much more concrete to say, I'm going to start the experiment, and before I start the experiment, I will use this level of evidence. And once you've stated that level of evidence, that's it. That is your type of error. And then the p-value must be compared to that. The p-value should not be used to define that. All right, well, I never move as fast as I want to. So all those, let's just walk through a quick example. Suppose again, this is just one of the teaching examples. All right, if men and women, let me just see how much you call it. I'll try to finish it up in 5 minutes. If cholesterol levels do not differ between men and women, how many probability distributions are hiding in the data set? If there is no difference between them, how many probability there would be 1 probability distribution? There's only 1 probability distribution. If men and women actually do have different levels of cholesterol, how many probability distributions should I look for? 2, right? I'm going to start out with that belief. I'm going to start out with belief there's only 1, and I'm going to look for evidence of 2. Before I start, I'm going to say I'll live with a 5% chance that I'll accidentally conclude that there are 2, when in fact there are only 1.
All right, just to clarify, the null hypothesis here would be that the cholesterol levels are exactly the same for these 22.
I would say that they're all coming from 1 probability, exactly the same, but imply no variance to me.
Right. Okay.
No, I cannot say exactly the same. I can say they're all coming from 1 common distribution. Men and women have the exact same distribution.
That exact same distribution. Okay.
And see, here's this. Let's go to this, okay? So I collect my data. I just do a small experiment. I have 12 men, 10 women. We're doing total cholesterol, 220, 215. Here's my variances. Notice right back to where we began. All I really need is the mean and the variances, and I can play games all day long. And I can make judgments between probability distributions. Now, let me ask you this. So the mean, mu, is just the Greek symbol to say, where's the center of the distributions? That's all I'm asking. If they have the exact same center, they're lining up right over the top of each other. So there's one distribution. I'm assuming equal variances. So that this says the two means are equal, therefore I can model it as one distribution. This other one here says, no, U1 is not equal to U2. That means there is technically two separate distributions. There's two centers out there that I've got to go study. I get all my data, I summarize it all up, and then I say I started with a reasonable doubt of 0.05. Here's my evidence. Is this evidence beyond a reasonable doubt? Yes, that is evidence beyond reasonable doubt. The probability of observing my data is 0.0142. That's how likely this data was if I insist on believing there's only one distribution. That seems a little rare to me. That's rare enough for me to stop believing the first and jump to the second. That's all it is. I could be making a mistake. Never will know. But I have to make a decision, and all I'm going to say is, based on this experiment, the evidence leads me to believe or conclude the alternative. That's it. But there should be two probability distributions. Two probability distribution implies men and women are having different distributions. That they do not, that women may have a lower level. How would I write there? I'm very dogmatic. And in fact, you go find my articles and you'll see I put sentences in that I don't just give them a table and let people go and interpret. I want them to be able to read. I come in and say, there is sufficient evidence. I say, it's evidence at a time point error of 0.05 to reject the null and conclude that the mean cholesterol levels differ. It implies that there's two probability distributions. Then I come in and say very clearly, the probability of observing the data, or data more extreme, assuming the null hypothesis, or assuming, I should probably write in the journal, assuming that men and women have the same distribution, is only 0.01. And I summarize it. And then I gotta let the scientific community digest it and debate it. Okay? With all that, that's going to come in for another day. In fact, I thought I took these out. Now, I'm going to hold that for next week. Okay? Give you 8 minutes now. Okay? All right?
And so what if you said it the other way? So now if you go back to that slide.
I'm going back.
So are you saying there that the alternative hypothesis, there's a 99%?
No, I am not.
Okay.
No, I am not. That's a key point. No. All right? No, that is not what I'm saying. And some people do make that mistake. What you did there is, if you change the condition, the probability of the data given the null does not have to be 1 minus the probability of the data given the alternative.
Okay. You're just rejecting them.
That's exactly right. That is, what you just tried to state is not a mathematical truth. Now, if we said the probability of A given B plus the probability of not A given B, and kept the conditions the same, I kept the conditions the same. That's when they summed it. But you switched the conditions. You went from data given null to data given alternative. All bets are off now. Yes, ma'am.
So I was wondering how you were able to assume that even if the means were the same, that the variance.
I would come in and I would look at box plots. There would be a lot of tools in my background. But typically, what I do, honestly, is anytime I'm doing a 2-group test, I default and say the variances are not equal and adjust the calculation. Okay? All right. Talk to you later. I'm already tired. It's only 7 a.m. Thank you.
mean and standard deviation.
I don't know what it is.
One I've seen a lot of percent.
Oh, of course, you.
All those one for the report.
No. Standard error does not make sense. Standard error does not describe the population. You need to report standard.
Standard deviation is good.
Standard deviation, correct.
Thank you.
Uh-huh. Can I go home now? Oh wait, we got a forum.
What? You got what?
We got a forum tonight.
Yeah, there's a